Okay, so before we start topic three, here are kind of the big ideas for the day. So, really, what the focus of this topic is going to be is how we actually deal with an earthquake once it's happened. How do we, as human beings, start to prepare for it, know when it's going to come, know where it's going to go? Okay, so the focus of today is actually how we handle once an earthquake has happened. So, the big ideas for today first, okay, what is a seismometer? Okay, what is a seismogram? How does the SP time interval tell us the distance to an epicenter? How do we use that? And how does triangulation work? Just kind of in general, what's the process there? So the next kind of portion of this is when an earthquake happens, we figure out where it is. And then by extension, once we know how far away it is, we can figure out how long it's going to take to get there, right? And even how bad it will be once it does get there. How much do we need to worry? Okay. So this is a seismometer. Okay, so think about that ending, meter. That usually means a tool used to measure something, right? Think about it. A thermometer or a thermometer measures temperature, right? A barometer measures pressure. An odometer in your car measures distance, right? So that ending meter means measures. And seismo, as we know, means earthquakes. So a seismometer basically measures, well, earthquakes in the form of measuring seismic waves. So essentially what a seismometer is essentially just, it's nothing that fancy actually, it's just a pen on a weight, okay, attached to something via the string, right? The string attaches it to this thing, which of course is connected to the earth because it's just sitting on the table. So this kind of base here is sitting on the earth. When the earth comes in and shakes, this pen is weighted so that it will always kind of just face down. And the paper just kind of keeps scrolling along like a treadmill almost, right? The paper just keeps scrolling and scrolling and scrolling. And so if there's no earthquake, well, then this isn't shaking and this pen just kind of draws a straight line, right? So no earthquake. So no earthquake would just give us a straight line. But when the whole earth starts shaking, okay, this starts shaking. I know you might be thinking, well, wouldn't this shake too? But it actually doesn't because of the heavy weight, right? So the heavy weights resist motion so that this stays still while the rest of the earth is kind of shaking. If you don't believe me, I've kind of made my own seismometer here that I've used before. Usually, in Science 20, I actually even get some paper out and I pull it and show you what happens when an earthquake happens. But essentially, watch. This is just a heavy weight, it's just a pen attached, right? Essentially, what I've made here is a seismometer. So you can see the weight kind of keeps it down, right? Right. As my hand shakes a whole bunch, the weight actually stays pretty constant. Look how much I'm shaking. How much I'm shaking, and the pen is actually staying pretty much in the same place, right? At least compared to how much the earth is moving around it. So as the earth shakes, the pen is just kind of staying in one place. And so as the paper moves through, right, it kind of starts to record the shaking of the earth. Okay. And so the piece of paper, what's going to be actually produced by a seismometer, that's called a seismogram. So a seismogram is the piece of paper itself. So that will actually show, right, no earthquake, no earthquake. First waves arrived. Do you remember what the first waves to arrive would be? The P waves, right? Then the S waves, which are a bit bigger, right? And then the surface waves, which are the biggest of all. Okay, so the piece of paper is called a seismogram. So a seismometer makes a seismogram. Okay, so you can kind of see here, these are 5 seismograms, all produced from the same distance from the same earthquake. And you can kind of see the difference based on where they were sitting. So this kind of leads back to what we were talking about when you're building buildings, right? When you're making structures, you need to be aware of what kind of seismic activity you're going to be dealing with. If you live in a place where there's never going to be any earthquakes, you don't need to worry about it as much. But if you're living along the San Andreas Fault down in Southern California, for example, right? Well, then, yeah, you need to be very conscious of where you build. So you can see here, bedrock, right? That's the most solid foundation kind of thing you can build on. And look, from this earthquake that was built, if this building were built on bedrock and there was a seismometer in it, that's the kind of shaking they would actually feel, right? Zone 2 is on stiff sediment. So sediment is basically any ground up small rocks. So things like sand, silt, okay, mud, those are all sediments. So if you have slightly stiffer sediment, like maybe clay, right, it's a little more sturdy and you won't get as much, but you can see as it gets more and more, we get to the point like mud, right? That's going to be soft sediment and you're going to get big shaking happening there. So these are all examples of seismograms. Okay, great. So we use these to detect shakes in the earth that sometimes we can't even feel, right? But a seismometer can actually pick up even really small ones. They're very sensitive. If we detect that, technically all we know so far is that there's an earthquake, right? We just know, okay, somewhere there's an earthquake. That doesn't help you much, right? If I just say to you, hey, there's a spider, right? You're going to go, well, where? Where's the spider? Okay, so we have to now use that information to figure out where it is. How do we do that? It comes down to knowing the speeds, right? So remember last time we talked about the wave speeds. So of course, P stands for primary, so they arrive first, then the S waves, then the surface waves, right? 1, 2, 3. So remember, fastest to slowest goes P to surface, but also least damaging to most damaging goes P to surface. Okay. Here's the thing. We know how fast they go. Average speeds are known. We know how fast a P wave goes. We know how fast an S wave goes, and we know how fast surface waves go. Okay. We have all of those speeds down pretty pat. Now, just knowing the speed of one type of wave and it arriving doesn't necessarily tell you how far away it came from, right? Or where it came from. Imagine we're walking down the street and someone drives by us in a car going 100 kilometers per hour, and I say, okay, students, that car just passed us at 100 kilometers per hour. Where'd it come from? Well, you would all go, what? Doesn't tell. We have nowhere near enough information. It could have come from down the street. It could have come from Calgary. It could have come from California. Who knows where it came from? All we know is that it's here now, right? We know it doesn't help us to know how fast it's going. All we know is that it's here now. Okay. So what we need to do is figure out the difference in waves arrival times. Okay. So to kind of analyze this, I'm going to ask you to imagine me and you are both going to go somewhere. Okay. We're both going to go on a trip. Now, me, I'm going to get in my car and I'm going to drive. You, on the other hand, are going to get on your bike and bike there. Okay. And so we leave the school and we start driving and we start heading to where we're going. Okay, so we leave at the same time, just like seismic waves all leave at the same time, right? Because the earthquake happens and all the waves leave. It's just the difference is how fast they go. The same way we're going to leave the school at the same time, but the difference is that me in my car, I'm going to go a lot faster than you on your bike, obviously, right? Now, if we don't have to go very far, let's say our little trip is going to be to the McDonald's, okay, the McDonald's in Thickwood from the school. Well, I'm still going to beat you there because I'm faster in a car, right? But really, you're not going to be that far behind me. So if we don't have to go that far, that difference in our speeds, it doesn't really add up to much, right? I don't get that far ahead of you because we didn't have to go that far anyway. So a big difference in speed didn't mean I arrived that much sooner than you. Okay, now imagine we're going to drive to the Gregoire McDonald's. Okay, well, now we've got farther to go. Now I'm going to pull ahead of you quite a bit. I'm going to get to the McDonald's, I'm going to order, I'm going to eat before you probably get there. So a farther distance meant that the gap between us grew, right? We got further and further apart because I was faster than you and we went a longer distance. Okay, now imagine I'm in my car, you're on your bike, and instead of Gregoire, we're going to go to Edmonton. Well, now we're looking at, I'm going to get there in about 5 hours. You're probably going to take at least a day to get there on a bike, right? Now that gap is really starting to grow. So, so the farther we went, the bigger the gap between my arrival and your arrival, right? My arrival in a car and your arrival on a bike. To McDonald's, I probably only got there maybe a minute before you, right? The Gregoire McDonald's, I probably got there at least like 20 minutes before you, right? And now Edmonton, we're talking, I'm getting there like 15 hours before you, at least. That's kind of what happens with P waves and S waves. P waves are me in my car, they're much faster. S waves are you on your bike, they're a lot slower. They're still the second fastest, right? They're faster than your friend who's walking. They would be the surface waves, okay? But the fact remains, if I'm faster than you, the gap between us is just going to get bigger and bigger and bigger the further we actually travel. That's the idea here. The farther away a seismograph is from the focus of the earthquake, so that would be the school in our example, right, where the waves start from, then the longer the gap between the arrivals of the P and S waves. This is called the SP interval. So if the earthquake is very far away from us, then the P waves will get there. And then we count and we count and we count and we say, oh, okay, there's the S waves. It's a little bit like when you were younger. Did your parents ever tell you, count the time between the lightning and the thunder, and that can tell you how far away the storm is? It's actually the exact same idea, right? Since light is faster than sound, by counting the difference between their arrival times, you can figure out how far away the storm is. Same thing here, because P waves, those are like the lightning. S waves, those are like the thunder. The longer the distance between them, well, then the farther those waves must have had to travel, and the bigger of a lead the P waves got. Okay, so notice that here, the SP time interval, right? That's the gap between the P waves arriving and then the S waves arriving. So when those P waves hit, we're kind of in a moment of, it's kind of a little bit scary, right? We're hoping that it's a long, long time for the S waves to arrive so that we know, okay, it's pretty far away, right? If the P waves arrive and then the S waves arrive right after, we know that's a very close earthquake. If you've ever been in a thunderstorm where you see the lightning and hear the thunder at the same time, you know that thunderstorm is like right on top of you, right? Okay. Which is good, because the longer the P and the S waves are, then the longer we have to prepare for the really damaging surface waves, right? So to go back to our other example, if I'm driving, you're biking, and your friend is walking, right? And your friend who's walking is the most damaging, right? People are going to be happy when they see a big gap between me and my car and you on your bike, because now they know they have lots of time to run away from your friend who's walking behind us and very damaging, right? If they see you right behind me, then they know, uh-oh, that means they didn't come from very far away, because Mr. Maxwell hasn't got very far ahead in his car, which means the destructive friend, is coming right behind them. So this is actually a graph that seismologists would use, okay? Notice how on this axis here, we have distance. For some reason, this one, the distance gets bigger as we go down. That's not like most graphs, right? But notice up here, 0. So this is right at the epicenter. Okay, that's right at the epicenter. And then as we go this way, it gets farther from epicenter. And look at this, they've used real seismograms to show us what it looks like, right? So again, we don't know. The P waves arrive and we're stuck kind of counting, going, okay, where are those S waves? Where are those S waves? And the longer it takes us, the farther away we know the earthquake is. So you can see here where it's the closest one, right? The P waves, they should be, this is just a DT graph, right? This is a DT graph for a P wave. We say, okay, it arrived now, S waves arrive now. Okay, so there's this much of a gap, right? And that means we know we're this far away. Here we say, as we get farther away, look, okay, there's the P waves, and see how there was a longer time now? See how this here is bigger than this here, right? So that means it's farther away, bigger SP time interval, further distance away. Notice how this one's even bigger, right? These are all SP intervals, okay? It's just the gap between the S and the P. It's the time that you count between the lightning strike and the thunderclap. And then notice what happens as we get farther away, the longer now we have to prepare for the very damaging surface waves. Notice the surface waves are the most damaging. Notice how they're the biggest in each seismogram, right? They cause the most motion, okay? Okay, so using that gap, we can figure out how far away it is, okay? But is that enough information to actually say where it is? Because again, it's important to know, right? If you are, right, if people in Edmonton detect an earthquake and they say, okay, I found an earthquake 400 kilometers from here, right? Well, we're in Fort McMurray. That's 400 kilometers from Edmonton. We kind of need to ask Edmonton now, well, hey, is it 400 kilometers north from you, or is it 400 kilometers south from you? Because if it's 400 kilometers north of you, we're in trouble, right? It's a very different scenario depending on which way it is. So knowing how far it is great, but it doesn't necessarily tell us where it is. So that's kind of the final step here, right? If I tell you, hey, there's a spider in my room, at least now you know roughly the area that it could be in, but you still don't know where exactly it is, right? Which you would like to know. So how we do that is actually really cool. We take the SP interval from 3 different locations. Remember, the SP interval tells us how far it is. Okay, so for example here, in Mexico, they've recorded an earthquake. They've felt one. And they say, okay, we did the math. We took our SP interval and we said that it was 900 kilometers away from us, okay? But there are a whole bunch of places that are 900 kilometers away from that place in Mexico, right? You could go north, east, south, west, 900 kilometers, and every direction in between. So how many points are there that are 900 kilometers from that station in Mexico? Well, every single point on this circle is 900 kilometers away from that station, right? This is 900 kilometers. This is 900 kilometers, right? The whole thing is 900 kilometers away. And so what we do is we say, okay, well, we know it's 900 kilometers away. We just don't know which direction. So let's draw our circle. So we'll draw a circle 900 kilometers away from us, and that it is somewhere on that circle. Okay, that's not bad. All right. So we have a big circle, but again, imagine you're living here in Florida, right? And Mexico tells you, well, 900 kilometers away from us, there's a epicenter of an earthquake. If you're in Florida, you're going, well, which way do I need to get ready for some really bad surface waves, or could it be over here? Which still, I should probably brace myself, but that's a lot different, right? And so, not bad. But if we can get another place to figure out how far away it is, so this one would be from Isla Socorro. Okay, if we go to Isla Socorro, just another station in Mexico, and they say, okay, we did the math on our SP interval, and we found that the gap was a little bit bigger, and the math worked out to be about 1,800 kilometers away. So again, that's 1,800 kilometers, that's 1,800 kilometers, that's 1,800 kilometers. So you draw a big circle with a radius of 1,800 kilometers, okay? Because every point is going to be 1,800 kilometers away. And there we go. Okay, so it's somewhere on this circle. But hang on, we already said it was somewhere on this blue circle, and we know it's somewhere on this red circle because it's 900 kilometers away from here, and it's 1,800 kilometers away from here. Okay, so what does that mean? If it's on both of those circles, then it has to be where they intersect. So now we have two options. It could be here, or it could be here. And I know you can tell the answer, right? But pretend that green circle is not there. It could be where the red circle meets the blue circle there, or where the red circle meets the blue circle there. Not bad. We've now pinned it down to two locations, right? Pretty good, considering before we didn't know where it was at all. It's in one of these two places, because those are only the two places that satisfy both of the criteria we know, right? So we need to narrow it down once more. If we can eliminate one of those two places, so what do? We say, hey, Pennsylvania, what did you get? Well, our SP interval was way bigger, and when we did the math, we found that it must be 3,300 kilometers away from us because there's a 5-minute gap between the S waves and the P waves. And so we go, okay, well, then we'll draw a really big circle, 3,300 kilometers, find every point on the globe that is 3,300 kilometers away from this station, and what do you know? There we go, right? It must be there because that's the only point that's on all three circles. This process is called triangulation. Why tri? Well, how many wheels does a tricycle have? 3, right? How many sides does a triangle have? 3. So how many circles did we draw? We drew 3. It's kind of a cool fact about our universe. There is only one point in space that is 900 kilometers away from here, 1,800 kilometers away from here, and 3,300 kilometers away from Pennsylvania. There's one point in the whole universe that satisfies those conditions. Okay, we live in a 3-dimensional universe, you've heard, right? That's what that means. It means you only need 3 coordinates kind of to pinpoint where you are. Okay, this is actually exactly how the GPS on your phone works. So if one satellite can make contact with your phone, your GPS won't work. If 2 satellites can make contact with your phone, your GPS won't work. You need 3 satellites making contact with your phone. It works exactly the same way, right? If one satellite can contact your phone, it says, okay, well, all I know is that Mr. Maxwell's somewhere in this circle away from me. If 2, they would say, okay, well, Mr. Maxwell's either here or here. No good for me on GPS, right? I need to know a little bit better. If you're trying to give me directions to McDonald's, I need to know whether I'm here or here, obviously, right? And so if a 3rd satellite can make contact with your phone, then your GPS will work. That's why GPS doesn't work as you kind of go away from where we have satellites more heavily concentrated in orbit. Either way, okay, so the point is, if at least 3 circles are drawn by 3 different monitoring stations, okay, and what are these circles? Where the radius equals the distance, the epicenter will be at the point where all 3 circles intersect. This is called triangulation, right? Knowing where the earthquake actually started from, it allows us to predict not only when, but where the dangerous surface waves will arrive, right? If this was an underwater earthquake, again, important to know, right? If the earthquake had happened over here, that means water was getting displaced, and these people might need to be getting ready for a tsunami, right? Since it happened here, kind of on the coast, there probably was not as much water to displace, and we're probably safe. So that is very crucial to know, right? In the case of underwater earthquakes, it allows us to predict tsunamis. This allows communities to prepare and evacuate if necessary. This really does save lives. And so I'll throw these back up. That actually wraps up topic 3. So what kinds of events can lead to a tsunami, right? Remember, anything that can cause a big displacement of water, just think about those. Okay, what is a seismometer? What is a seismogram? Related but different. How does the SP time interval tell us the distance to an epicenter? And how does triangulation work? Okay, if you're looking for practice with this stuff, you could do the topic 3 section of the formative work for the week.